Okay, so this PowerPoint that I'm showing you, it's posted on the Schoology website in the Waves folder. It's entitled Sounds. You'll see it. It has a lot of animations. I'm not quite sure that they still work on whatever you guys have to use them to view. So I'll play just a few slides here showing you the specific animations. We took a look at this right here. This is what the air particles would look like if a sound wave is generated, because especially by a speaker, because all sounds are generated by vibrations, and the speaker goes forward and back and forward and back, and it squeezes the air and stretches the air out successively. The wave travels that way, and basically if this is your eardrum, this is how your ear responds to sounds. So essentially what we're looking at is a linear slice of the wave, because the reality is this, is that sound doesn't travel in a straight line. And if you think about that, what we want to think about is the fact that, if there is a speaker here and it's emanating out some sound, a person here will hear it, a person here will hear it, a person here will hear it, and a person here will hear it. And if the speaker's loud enough, they're all going to hear it. And they're all going to hear essentially the same thing as well. Although it could be a little bit different, because the person here, we know that they're going to hear something that's a lot louder, and simply because they're closer, but they'll still hear the same sounds. It's just going to be a lot more intense, if you will. The amount of time it takes for sound to travel to someone's ears is very, very quick. In fact, I think we talked about this. At room temperature, the speed of sound is 343 meters per second. So essentially that's for air. And there's a lot of different medium that sound can travel through. There's this table here on the PowerPoint shows you that when the air is actually colder, it's going to travel a little bit slower, and that's because the air particles aren't moving quite as fast anymore, so it takes longer for them to transmit that energy from one particle to another. Helium, if you take a look at it, 970. So helium is a gas that actually moves very, very fast, and you can see the speed of sound's greater. It also has consequences. It makes your voice really high if you happen to breathe it in. It actually travels a lot faster in water. There are certain animals that can talk to each other underwater, like dolphins and whales. Submarines send pings through water. It travels quite a bit faster in water because those particles are a lot more closely packed together, so they can transmit sounds a lot more rapidly. And then if you take a look at the solids, it travels even faster in solids. We're probably going to restrict ourselves to air for the most part. And what I want to show you is actually, if this is our sound source, this is a new view of what a sound wave would look like, so that everybody around it will hear it. Typically, if we could see the particles, they would look like this. And you can see that what we were doing is we were kind of looking at just a slice of that wave like this, but now we get to see the whole wave. And this explains how it reaches everybody that stands around the source itself. We represent this figure, because this is obviously way too hard to draw, by showing you the crests of the wave, which are the most closely packed spots of the air particles, and you represent them with lines. So this would be another representation of that wave radiating outwards in all directions from that central point. And so when we're looking at the crest of the wave, crest to crest is always the wavelength, so you can get the wavelength of the wave essentially. So this is an important picture to show us that sound can reach everybody's ears, but it's also an important picture to explain why everybody will hear the sound differently in terms of the intensity that source registers on each person's ears. So let's just say that this is a 30-watt speaker. Basically, that is the power of the speaker. Every speaker has a certain amount of watts to it. 30 watts is actually quite loud. But there's no question that this person is not going to hear it as loud as this person. And if I draw someone farther, they're not going to hear it as loud as this person or this person. So it's definitely related to distance. This is the idea of intensity. Intensity is the power of the source divided by 4 pi r squared. That may be recognizable to you guys. This is the surface area of a sphere, and if you think about it, this sound is radiating outwards in spherical fashion, all three dimensions. So what we're doing is we're spreading that power of the source over like a spherical, shell. And the farther and farther we get, the larger that spherical shell is as it radiates outwards. So this explains why this person's not going to hear it as loud as this person, because the power of the source is 30 watts. Say this guy's 1 meter away, say this guy's 2 meters away, say this guy's 3 meters away. They're all going to hear something different. And we'll just do the quick calculation to show you what it's going to look like. What you may notice is that this is dying off as an inverse squared law, kind of like we've seen with the force of gravity here. They all are listening to a 30-watt speaker, but this person right here, it would be 30 watts over 4 pi times 1 squared. If you're doing this in your calculator, I highly suggest you put that whole denominator in parentheses so that you get your order of operations correct. And if I type in the numbers, let's see what we get. I get 0.238 watts per meter squared. That's our unit for intensity. Believe it or not, and we'll take a look at the decibel range in a little bit, that's really, really loud. That was for person 1. The person that's 2 meters away, still 30 watts, but now it's 4 pi over 2 squared. So we've doubled the distance. And what you're going to find is that this person hears something 4 times as intense. So you got 0.05968 watts per meter squared. We'll do person 3. 30 over 4 pi, 3 squared. And putting that number in there, they hear 1/9 of the original person, so 0.0265 watts per meter squared there. And again, that's actually pretty loud. You guys may be familiar with decibel readings. Some people on their home stereo system, it'll tell you how many decibels that you're probably listening to. There's this thing called the decibel scale, and I want to show it to you. Based on the intensities that you have, and they're all in scientific notation here, we can think about the quietest thing that you could ever hear in your lifetime. Maybe a pin dropping. That's going to be a very small intensity, 1 times 10 to the negative 12 watts per meter squared. That's what we call the threshold of hearing. If you are, let's say, 3 meters away from a person and you can hear them breathing, and I'm not talking like a heavy breath, I'm talking like a light breath, that'd be 1 times 10 to the negative 11 watts per meter squared. Whispering quietly at 1 meter, 1 times 10 to the negative 10. If we're back in the classroom and nobody's talking when they're taking a test, 1 times 10 to the negative 9. Ambient noise on the street without any traffic, 1 times 10 to the 8. You can go through all these and you see that as we get louder and louder and louder, something like Niagara Falls, which is really loud, 1 times 10 to the negative 3. And then what we were talking about was, listening to that speaker, that person 1 meter away got 0.23 watts per meter squared. Well, this is a home stereo at max volume, right? That's deafening. So 0.23 watts per meter squared is something you don't want to hear. And then if you take a look at the intensity, it gives you how many decibels there are. The smallest thing you can hear is 0 decibels. And every time we go up by a factor of 10 intensity, we get 10 more decibels. Go by another factor of 10, you get 20 decibels. So every time this is multiplied by 10, this goes up by 10. And that's because it's a logarithmic scale. So let me just show you how the decibel scale works. If you take a look at that formula on the PowerPoint, the one that I just had on screen there, the decibel scale is a logarithmic scale. So the symbol for it is beta, and it is 10 times the log, and our base is 10 here, of the intensity that we're hearing over I0, where I0 is the threshold of hearing, that pin drop sound. I0 is always 1 times 10 to the negative 12. That's a constant. So we can plug in our value for I, and we can get how many decibels that is. And then if you take a look here, a really loud rock concert's 120. Threshold of pain, where you physically hurt hearing something, that's 130. So if we go back to those numbers that we had for intensity, we had 3 intensities here. This person at 1 meter away is 0.238. At 2 meters away, 0.05968. At 3 meters away, 0.0265. Anyone that's ever been really close to a very large stereo speaker knows they don't want to be near it all that long. So if I do the beta value for person 1, the decibels that they're going to hear, it's going to be 10 times log base 10. And we're going to do an I of 0.238, and then this is 1 times 10 to the negative 12 in here. So all that's in parentheses. So 10 times log 0.238 divided by 1 times 10 to the negative 12. And one thing I need to stress here is that you expect numbers to always be above 0 here. Somewhere usually between 1 and 120. This person gets 113 decibels. So that's pretty loud. We'll go back to that scale in just a second. Let's do the other 2 people. I'm taking a look at the other 2 people. We have their intensities. So we just have to put in the different value for I here. All I got to do is I got to put in 0.05968 instead of the 0.238. So switching that intensity, I get 107 decibels. Still pretty loud. The third person, let's put in their intensity. It was 0.0265. And I get 104 decibels. So if you have a large stereo speaker, chances are you don't want to be 1, you don't want to be 2, you don't want to be 3 meters away. You want to be something pretty far away. And let's just go back to that table really quickly, and then we'll leave it at that. If you look at this table, what you see is that, you know, if I'm taking a look at the rates of sound here, or the loudness of the sounds here, I would say that normal conversation 1 meter is okay for me. Busy traffic's not that bad. If you're operating vacuum cleaner, that's loud. So somewhere above 70 decibels is what I would consider pretty loud from a personal level. So hopefully you have an idea about how intensity works now.